Hey everyone, and welcome. Today, we are going to dive into a concept that's, well, pretty fundamental to how just about everything works, from a tiny puff of gas to the entire universe. We're talking about internal energy. It's like this hidden power packed inside every single bit of matter, and we're about to unlock its secrets. So I want you to picture this. You've got a sealed box, and it's just full of air. I mean, it looks pretty empty, right? Inactive. But what if I told you that inside that box, it's absolutely buzzing with a huge amount of unseen energy? That's really the question we're tackling today. What is that hidden energy, and how can we even begin to understand it? Okay, so to even start, we have to draw a boundary. You know, in science, you can't just study the entire universe all at once. You've got to define exactly what piece of it you're looking at. You have to create what we call a system. And that's all a system is. It's our little world in a box. For what we're doing today, our system is just the gas molecules trapped inside that container. Everything that happens with those molecules, that's what we're interested in.
So, now that we have our system all defined, we can get to the real heart of the matter. What exactly is all this energy buzzing around inside our box?
Well, it has a name. It's called internal energy. You'll often see it represented by the letter U, and it's basically the grand total of all the energy tucked away inside our system. Now, this total energy really breaks down into two main flavors. You've got the energy of motion, that's kinetic energy, and you've got the energy from interactions between molecules, which is potential energy.
And this simple equation really spells it all out. The total internal energy, U, is just what you get when you add up all the kinetic energies and all the potential energies of every single molecule zipping around in there.
Now, to make all of this way easier to wrap our heads around, scientists do something really clever. They came up with a simplified model. They compare a real gas, which is kind of messy and complicated, to this perfect, simplified version called an ideal gas. Let's see why this helps so much. And here it is, the key difference. In a real gas, all those little molecules are attracting and repelling each other. That creates potential energy. But in an ideal gas, we just pretend those interactions don't exist. We simplify it. And by doing that, the potential energy becomes zero. And that right there is a game changer, because it means for an ideal gas, all of its internal energy is only its kinetic energy. It's all about motion.
Okay, so if the internal energy of our ideal gas is just about motion, what does that motion actually look like in the real world? And more importantly, how do we measure it? So let's just pause on this for a second, because this is the key to everything that comes next. For our simplified ideal gas, internal energy is purely a measure of how much its molecules are zipping and bouncing around. It's that simple.
And right here is where it all clicks together. The more motion you have, the more kinetic energy you have. And what do we call the thing we measure that tells us the average kinetic energy? Temperature. So for an ideal gas, internal energy is directly tied to its temperature. If you heat it up, all you're really doing is making its molecules dance faster. But wait, there's another layer to this. It turns out not all molecules dance in the same way. The actual shape of a molecule changes the different ways it can move and store all of that kinetic energy. These different types of movement are called degrees of freedom. So a really simple molecule might just move from point A to point B. We call that translational motion. But a more complex one can also tumble and spin around, which is rotational. And some can even vibrate, with their atoms stretching and compressing almost like they're on tiny little springs. And as you can see in this table, the more complex the molecule, the more of these degrees of freedom it has. A single atom gas, like helium, can only move side to side, up and down, and forward and back. That's 3 degrees of freedom. But a 2-atom molecule, like oxygen, can also spin in a couple of ways, adding 2 more. And that formula on the right just shows how this all connects to internal energy. The big takeaway is that a higher number of freedoms means more energy can be stored at the very same temperature.
Okay, so all of this leads us to one final and really fascinating paradox. If temperature is really just a measure of molecular motion, what in the world happens when you get to the coldest possible temperature there is?
The question is pretty straightforward. At absolute zero, that's 0 on the Kelvin scale, does everything just stop?
I mean, it seems logical, right? If you keep pulling heat out of a system, you slow the molecules down more and more. So at 0 heat, you should get 0 motion. Makes perfect sense. But get this. That's not what happens at all. It turns out that even at the absolute coldest theoretical point, molecules still have this tiny minimum amount of kinetic energy left over, and this is called zero-point energy.
So the big mind-blowing fact here is that motion never completely stops. Even at the coldest temperature you can possibly imagine, there's a fundamental, unremovable jiggle to the universe. The kinetic energy never actually gets to zero.
And that leaves us with a final thought to chew on. If energy and motion can never be totally extinguished, not even at absolute zero, what does that imply about the fundamental nature of energy, and maybe even the universe itself? What does it mean that there's always this baseline hum of energy, no matter what?